Hello, everyone, and welcome to the AI Explorations podcast. My name is Rajesh. Today, I'm going to be discussing a very interesting paper with you. The title of the paper is The High Interest Credit Card of Technical Debt in Machine Learning. The paper is authored by a team at Google, D. Scully, Gary Holt, Daniel Golovin, and many others. When you go through the abstract of the paper, it's kind of an interesting set of problems that they're trying to address: boundary erosion, entanglement, hidden feedback loops, data dependencies, and various other patterns that are within the machine learning systems engineering set of problems. They use the umbrella term technical debt to discuss many of these patterns and how they impact the uh, performance of machine learning systems of different kinds. They also discuss how we could potentially avoid some of these negative patterns and some of these negative influences in machine learning. There are 3 or 4 key themes in the paper, and I'm going to cover them in the order in which I find them to be interesting and important. The first of these themes is complex models erode boundaries, and the term that they use really to describe this phenomenon is change anything and you change everything. It's the holism versus reductionism debate that is rejuvenated essentially in the context of machine learning. Now, machine learning systems tend to be built as closely coupled systems of data, models, hyperparameters, training, and deployment systems. And because of the fact that you have so much of coupling across all of these different components, and because there are hidden feedback loops and changes that could happen at different points in time, it's quite likely that these changes propagate and move backwards through the system as well as forwards through the system. And this makes machine learning systems essentially complex systems where the impact of specific changes in the system is felt beyond the immediate boundaries within which we make those changes. Those impacts are felt upstream. If you're making a change in model formulation or hyperparameters, those changes propagate upstream to the data and they propagate downstream from the data. They could propagate upstream from the initialization or the training parameters or model metrics, depending on the kinds of training loops and feedback loops that we have built into our machine learning systems. The second aspect of this paper that really caught my attention was the fact that there are data and code dependencies that are both present in machine learning systems, but that the data dependencies are much more important and they have an outsized impact compared to the code dependencies. And I refer to this set of phenomena as the Hotel California checkout problem. And one way to succinctly and concisely describe what's happening here is by using the old popular line, I would say, from the song Hotel California, which is that you can check out any time you like, but you can never leave, which in the context of machine learning systems is indicative of the dependencies that old features tend to have on models even after those models have been retrained with new data. In a sense, by training a model on an existing data set, we build a sort of dependency into the features that are producing the model that you see. And the paper describes this in a much more lucid way, but I think that this term Hotel California checkout actually kind of summarizes the essential idea of that. Now, the next thing that I found to be important was the idea of a correction cascade. Within the data and code dependencies part of the discussion, the third idea that I want to discuss is the correction cascade. Now, the correction cascade refers to this phenomenon whereby if you want to make a change to a model and deploy that new model for a different use case, you end up having to change not only the specific thing that you wanted to change, such as maybe a hyperparameter of a model, but you end up cascading a number of changes that are related to that change through the entire system. And this, in a sense, goes back to what we talked about earlier about machine learning systems being closely coupled and the fact that those are complex systems as well. There is a common adage that goes, for want of a nail, a shoe was lost. And this is actually a set of ideas around how, when you're chasing that 2% or that 5% of additional performance that you want to eke out of a system, you might actually be compromising large parts of the system's performance just by going in the direction of making those incremental improvements. And in much the same way, machine learning systems improvement can sometimes result in this negative spiral of avoidable changes that cascade through the system as corrections. The next element or theme that's covered in the paper is system level spaghetti. There are three parts here again. The first one is glue code. Glue code is the term that the authors use to discuss how parts of a system that might be promising initially are developed maybe with the specific objective, and as experiments evolve and as new people build systems in that team, in that organization, and as the thinking around these use cases evolves, aspects of that code or aspects of those projects are taken and co-opted into these new projects. The end result of this kind of liberal borrowing of code and ideas is that we essentially build the equivalent of a caffeinated spider web of data science. And I use this term caffeinated spider web in the context of spiders that are effectively caffeinated. And literally there was an experiment done on this where spiders that were caffeinated were found to be weaving or random webs as opposed to spiders that weren't. And I use this analogy here because in a lot of enterprises where data science is being done, the data scientist is not normally building from scratch. They are building based on code that's already present. In a sense, the glue code that they use, it already provides them a starting point with which to start building their system. And because of the fact that it provides that starting point, there are numerous compromises that are made in terms of what abstractions are available for them to solve the problem, what their starting points are, and up until what point they can build a given system, certain performance constraints around the technicalities such as latency or accuracy metrics, or various other considerations that might form the set of things that the machine learning engineer is trying to look for when they solve these problems. Now, this glue code is closely associated with another phenomenon called pipeline jungles. Pipeline jungles in data and machine learning systems emanate because of this strategy of starting from a place of very good intentions, where enterprises want to build all of their applications on a given platform and only on that platform. And this is the normal mode of operation. The centralization is a normal mode of operation in many enterprises today. This isn't entirely a bad thing. If companies were to have heterogeneous systems, they would arguably have far more trouble handling those heterogeneous systems than if we're handling homogeneous systems for data processing and management. And the reason pipeline jungles become important in this context is, it's, as the adage goes, careful what you wish for because you might actually get it. They originally envisaged that there are going to be lots and lots of pipelines, each of those pipelines being meant to serve a specific purpose, whether that's data processing or whether that's machine learning or whether that's preparation of metrics for reports or anything else. The end result of that is that we actually end up having lots and lots and lots of pipelines. The benefit of having lots of pipelines is having many starting points from which to start building value in machine learning. If you want to do an experiment, you can start with an existing pipeline. If you want to build a new model, you can start with an existing model. The benefits of this are obviously quite significant, especially as you grow in complexity. The disadvantages, however, are that we have, number one, a paradox of choice. As Barry Schwartz says, the greater the number of options we have in front of us, the harder it is to decide. In much the same way, starting from hundreds of pipelines is actually a very difficult thing to do for a data scientist or a ML engineer who wants to build a specific model. So this is one aspect of the system level spaghetti and how this impacts machine learning systems engineering. There's a third consideration, which is the dead experimental code paths. And this has to do with literally the phrase cutting the cord in machine learning systems. What do you mean when you say cut the cord? When we say cut the cord, we essentially are weaning off a system to be able to be useful in the real world on its own. And in order for it to be useful in the real world on its own, the number of dependencies that the system has to legacy or dead code bases that are not being experimented upon has to reduce. It has to be ideally zero. This is never the case with contemporary machine learning systems. We routinely come across experimental code paths, applications which are no longer being maintained, languages that are probably not very popular, systems that are purpose built in specific underlying technologies without consideration for broader adoption, and various other computational considerations also, such as algorithms that are written with old paradigms of computing in mind, and other considerations around networks and the entire stack, really, all the way from processor up to the network and up to servers and APIs and what have you. So there are numerous experimental code paths in all of these areas of software engineering endeavor that influence machine learning development cycles. It's not so much the fact that they influence them badly all the time. It's just that when you build a machine learning system, you have to be prepared to cut the cord and enable it to function in production on its own. All systems have incipience, development, and decay, and with machine learning systems it is no different. With machine learning systems, however, the increasing need is that we should be able to build them in a way that resonates with the target audience, with the process owners and the customers, so that they're able to deliver value for them. And doing this with dead code bases or experimental code paths that may not be maintained is an idea that will soon be challenged in any organization. So these are a few of the observations I made from the paper, which is certainly a very interesting paper. Now there are a few observations that I have made more broadly, which I wish to share here. So the first of these is, does labeling and supervised learning in general implement fixed thresholds? So when I say fixed thresholds, they are referring in this paper to a very specific mode of operation, if you will. Enterprises that have been building data systems, they resort to certain rule-based or business rules-based approaches to labeling data or to building interactions in these systems. Now, when you build interactions like that, and then when you transition from that domain to a machine learning system, what happens is that you have to get used to the idea of dynamic thresholds, because machine learning is great at using the data and learning rules from that, which is the converse of software engineering, where you might have a set of domain rules and then you build a system that operates on those rules. With labeling and supervised learning, my own sense is that domain experts, data labelers, and other human agents that are performing this function of labeling the data so that it can be used to train machine learning models, these agents tend to have complex processing capabilities. when I look at a dog or a cat or a lamp or a computer or anything else, I have formed a sophisticated mental model of that object, not just from what I can see, but from various interactions. Now, it's common to think that since the operational domain of the algorithm is the visual domain, and since we can label these objects in the visual domain, we should be good, and the machine learning model in question should be sufficient. But I wonder if this approach extends favorably to different kinds of problem statements. For instance, if we have complex abstractions that we are trying to label, whether it's in sound or video, gestures, for instance, certain accents, certain figures of speech, more complex labeling essentially, right, is what I'm implying. My contention is that these more complex labeling techniques and methods don't necessarily scale when it comes to supervised learning. And it's certainly not an unknown fact that unsupervised learning is seen by many researchers as the future of machine learning. In many cases, and I recollect specifically a discussion with Ishan Mishra of Facebook on ML Street Talk and then on the Lex Friedman podcast. In both those conversations, there was a discussion around self-supervised learning for computer vision. Now, these are very interesting conversations to be having, and I think that labeling and supervised learning in general needs further exploration and further evaluation in the context of, do we build fixed thresholds or more generally fixed concepts through labeling and supervised learning. Now I'll move on to the second note or observation that I have based on what I've read in this paper, and that's the term technical debt itself. The term technical debt is used in the context of machine learning systems here, and we have, as I alluded to earlier, seen this term technical debt being used elsewhere. Now my question really is the term technical debt overloaded? We hear this term being used in a software engineering context, and in each case, the person who uses this term has a very specific reason for using it, and the reasons are quite different in different circumstances. That makes technical debt an overloaded term. It makes it a term that is in need of disambiguation. This is important because the conversation on machine learning systems is just getting started. And I think that as the years progress, we need to have more sophisticated language that allows us to communicate different elements of the patterns that we see, different elements of machine learning systems in general, and the very nature of ML systems as complex systems. We should be able to discuss these ideas and patterns with a lot more precision and a lot more clarity, and that necessitates the use of probably a slightly better terminology than the umbrella term that we see as technical debt. I don't mean to call out any specific writers in the industry or elsewhere, or people who use this term, because obviously the term is being used for a very good reason, because it represents something that is actually valuable and something that is important and worth paying attention to. However, I think where we are doing something right now that has a certain level of capability, we can do a bit better. And it's in this context that I mean to use terms other than technical debt. If you ask me for suggestions on what kinds of terms could be used in its place, I think that we have to break this problem down into very specific representations of what it means, what all these technical debt situations really entail. Other than that, I don't have a precise answer at this point, but it is something worth exploring. The third idea or note or observation that I want to share is something more general than just technical debt. we use many terms that are meant for software engineering systems in the context of machine learning systems. So I suppose a general question that I would have is, by using these measures of engineered systems, and by engineered systems I mean software engineering systems, are we using the wrong prism to study ML systems and their complexity? An extension of this thought is that there are other systems out there, physical systems, digital systems, and so forth, all of which have their respective characteristics, measures, parameters, and so forth. Various concepts abound in all of these systems. So it's worth considering whether, by building these ML systems through the prism of software applications, are we losing out on the richness of engineering domains and fields that are out there that we are able to characterize in a lot more detail or in a lot more finesse? If you take the example of mechanical engineering, automotive systems engineering, or aerospace systems engineering, there are both empirical results and theoretically proven results that are derived from very specific definitions of phenomena that might be analogous superficially, but which are explained very clearly when you get down to it. So I think there is a case to be made for using sophisticated terminology that is native to machine learning systems, and perhaps there should be certain discussion on these topics as well. And it is my own humble opinion, based on my limited experience, that there might already be many such terms out there that haven't gotten the attention that they deserve, that haven't become popular in the lexicon of machine learning, and which we probably need to popularize in the machine learning community as a whole. So that concludes this video. I really hope that this is only the first of many videos where I can share some of my ideas and experiences and thoughts on various topics related to AI, and certainly I want to be able to discuss many more papers going forward. So if you like this, feel free to go over to aiexplorations.in, which is my blog, and if you find anything interesting there, please drop a comment, or you're welcome to connect with me on Twitter, on LinkedIn. I'll leave the links below. Thank you very much.